Okay, so I'm going to tell you about adaptive assessments today, and I will talk about some of the work that we did at Illinois, and but I'm also going to talk just more generally about how an adaptive assessment works, and what you have to do to make a good one, and what the value of doing it, why you would want to do this. And are we recording? Are we good?
We are recording.
Okay, perfect. Okay, so I'm going to give you just the key takeaways up front so that hopefully, have some motivation of what we're talking about as we go. But the basic idea behind an adaptive assessment over a traditional paper and pencil test is that you can gather a lot more information about a student than you can if you just use a static set of questions. And the output of an assessment can be more than just a score, more than just 18 out of 20 or something like that. You can produce something far more useful that can be used for other purposes, such as helping the student catch up or give them a personalized learning path and so on. We'll talk about some of those things. But as great as adaptive assessments are, they're not easy to create. There's a lot of challenges and things you have to look out for that you might not think about when you're used to using a traditional type of paper and pencil test or an online version of such a thing. So what do we mean when we say adaptive assessment? So I don't know that there's a broadly accepted definition, but it's some kind of diagnostic tool. It's a sequence of questions that the student gets, and that sequence of questions is dependent on the order in which the student has answered previous questions and whether they got those answers right or wrong, right? So they follow a non-predefined path through the space of possible questions. That's what makes it adaptive. So some examples of a non-adaptive assessment, like I mentioned, like a paper and pencil test. Some examples of adaptive assessments. One is Numbus, which is where the image on the left is taken from their webpage. Another one is ALEKS, which Allison mentioned earlier, which is the one I'm going to tell you the most about today, simply because that's the one I'm most familiar with. And there's other examples out in the world. There's a graduate school entrance exam in the United States, for example, that is adaptive. So why would we do this? Why go through all the trouble of making an adaptive assessment when it's so much easier just to make a paper and pencil test and grade it and so on? And so as I mentioned before, we should be able to get a lot more information because we can selectively choose questions that we can gather more information. There's a paper and pencil exam. It's this fixed set of questions. They can either answer those specific versions of those questions or not. All we can do is basically count how many they got right. Adaptive assessment can be smarter about how it goes through the space of problems, and it can say, okay, I know the student can do maybe a medium difficulty problem. So I don't have to ask them about some easier concept that is already implied that they could do by doing this harder problem. So I can explore the space of what they could possibly do better. And then at the end of the assessment, I could perhaps have a list of skills that they can do and can't do versus just having a final number that I use to somehow place them. But ultimately, the point is we want to gather this extra information so we can do something with it, right? So, maybe we want to test that more accurately predicts whether a student will pass or fail a class. And we want fewer students to fail classes. So if we have an assessment that better predicts whether they're going to pass or fail a class, then we'll have better overall outcomes for our entire student population. Yeah. If anyone has any questions, feel free to ask me as we go as well. Okay, so how does an adaptive assessment work, right? So in theory, you can imagine student answers a problem, they get a harder one, they answer a problem incorrectly, they get an easier one, but how do we actually do this in practice? So one of the challenges I want to call out right away is just there's more than one way to solve a lot of problems. So if I ask a student to solve a system of equations like we have in the bottom left, there's a lot of ways they can do this. They can solve for one variable in one equation, plug it into the other one, sometimes called back substitution. They can use this thing called Cramer's rule, which is in the bottom right. They could, if they know about matrices and inverting them, they could invert the system matrix and multiply by both sides. Or they could just try and guess the right answer and then check if it works and so on, right? So just because a student gets this question correctly, they answer it correctly, we don't know what they actually knew or did. And even if we tell them to do it a specific way, right, we have no way of verifying or enforcing that they did it the way that we asked them to. All we know is that they were able to answer this question right. So it's not enough just to have a specific question and have it target a specific concept. We need to think about how the concepts relate to each other and how if a student answers one question, what that implies about what they may or may not know about these other techniques that we're interested in. And so when we write these questions for adaptive assessments, they work best generally when it's a free-form response and the parameters of the question can be varied so that I can give the student a different instance of the question, maybe if they get it wrong. Free form response is better because it reduces the chance that a student will enter a lucky guess, for example. So if it's a multiple choice question and there's 4 or 5 options, then they have a 1 in 4 chance or a 1 in 5 chance of just guessing the answer correctly. And that's kind of a high error rate if I'm trying to make a strong conclusion from whether they answered this question right or not. If they have a high probability of guessing correctly, then I might assume that they have better skills than they actually do. Also helps prevent some forms of cheating if that's a concern, because not every student gets the exact same version of the question. They get different numbers. For the paper and pencil test, especially if it doesn't change over time, copies of the test will proliferate and people will have copies. Students will, share copies of the test with each other and memorize the answers and so on. It's much harder to do that if the questions are parameterized. Another advantage is if at some point in the process, we think maybe the student made a lucky guess or a careless error, we can go back and ask the student another version of the same question and see if they can do it. And then if we want to give the student an ability or opportunity to practice doing certain problems, we can generate more and more instances of them so they can practice doing those problems. And then when they come back and take the assessment again, it won't be exactly the same as before. Okay, so that's great in principle, but let's go a little bit deeper and see how we would actually do this in practice. So what we would say is, let's say we have a few hundred concepts that are important for a given class, either to start the class or to finish the class. And for each one of those questions, we can assign some probability that we think the student can probably apply this concept or not. They can probably answer a question that requires this concept or not. So we have a set of concepts that we'll just call C, and we have a set of probabilities corresponding to those concepts. When the student answers a question that targets a specific concept or maybe multiple concepts, then what we do is we update our belief in the probability that they can answer all the related concepts, that we have some sort of prior knowledge of how the concepts are linked together. And then we can try and choose the next question to minimize the uncertainty we have on all these probabilities. So we can try and choose the next question in a smart way to gather as much information as possible. So once the student answers a question, we need to have some way of updating these probabilities. And this makes the whole process into a dynamical system. I have a vector of all these probabilities. The student answers a question correctly or incorrectly. I update that vector of probabilities by some rule, and then I proceed to ask the student more and more questions. So of course, if they answer the question incorrectly, then it's going to cause these probabilities to decrease. If they answer it correctly, it's going to cause the associated probabilities to increase. And this, of course, is why we need to be careful about not allowing the student to make lucky guesses or try and prevent careless errors, because that's going to cause all these probabilities to shift in the wrong direction if they either high or low, depending on whether they made a lucky guess or they made a careless error. But ultimately, the idea is we have this set of probabilities associated to each skill we're interested in, and we want to drive all those to either 0, the student can't do it, or 1, the student can do it with high certainty. Once we can do that, then we have a good idea of what the student actually knows and what they don't know. Okay, so I'm going to talk a lot about ALEKS just because it's the one I'm most familiar with and the one I've worked with in the past. I'm not currently affiliated with ALEKS in any way, so this is just for informative purposes. And I will admit my knowledge is probably a few years out of date on how ALEKS actually works. So there's probably some newer publications on their more advanced features and so on. But so I'm mostly going to reference a paper from 2003, which gives a really nice overview of how ALEKS works. And so ALEKS stands for Assessment and Learning in Knowledge Spaces. And knowledge spaces are it's a mathematical theory that's been developed over 3 or 4 decades that ultimately was applied to learning math and math placement by Allison and I and others. So for the mathematicians on the talk or in the room, a knowledge space is something called an anti-matroid. It's a set of all the concepts that you could learn and a family of subsets of that set that are the permissible or the feasible subsets that a student could learn. So, so if a student can solve a system of linear equations, they can probably solve a single linear equation, right? So it would be unreasonable for a student to be able to solve a system of linear equations, but not also a simpler, highly related problem. So not every subset of the possible set of concepts is actually feasible for a student to be able to do. And there's some properties that this anti-matroid has. It's closed under unions, and it has this technical condition that I'll explain in a second. But basically, if you have a feasible set, if the student has a set of concepts that they can do, then there must be another set of concepts where if I take one away, they can still do that subset of concepts. So there must be a way basically for them to learn one step at a time. So again, to try and put this into context here, the feasible set is, it's a possible valid subset of concepts that a student could understand. Each of these concepts has, every concept has one or more subsets where there's sort of one step away. So there's always a way if I want to learn a specific concept that I can learn a path all the way through. And then, in principle, a student, no matter where they start from, there's always a path to them learning all the possible concepts that we're interested in, but there's many, many such paths, basically. And these feasible sets are useful because, if I have 300 concepts, then the total number of possible subsets is 2 to the 300, which is just way too large to try and realistically deal with or build a system that can understand this. The set of feasible subsets is much, much smaller. And it's much easier to work with, both theoretically and in practice when you build a system like ALEKS. And this concept of a feasible set has a nice property that, because of this exchange property, that once I know what the student's feasible set is, I know all the neighboring concepts that they could learn next. So if I want to help them learn new concepts, rather than just say, okay, well, go read the next chapter in the book or whatever, I can say, there's these 4 things are the ones that you're most ready to learn next. And so that's how you can form a personalized learning path out of them. Okay, so let's make it a little less abstract and give some examples. So this is, again, I'm going to reference several things from this 2003 paper. These are just 6 hypothetical problem types that a student might encounter in a course that we would call elementary algebra. And they're related by this diagram on the right, which says, okay, if I want to be able to learn concept C, I must already have concept A as a prerequisite. And similarly, if I want to learn E, I must already have prerequisite B and prerequisite C as concepts if I'm going to be able to perform E. And if the ultimate goal is to learn F, then you can see, I could either start at A and walk my way to F, or I could start at B, or I could just do some combination of both of those 2 things. So think about all the possible learning paths that a student has to go from starting with not being able to do any of these concepts to be able to do all of them. There's a lot of different paths that they could take. And if you follow these paths, you would form the subsets of these. This would give you the subsequent feasible sets. So knowing nothing is a feasible set, knowing A or B is a feasible set, knowing A and C is a feasible set, knowing A and B is a feasible set. And these are the different possibilities you can get there. Okay, so let's take these are just 6 questions. This chart was just a hypothetical relationship of these. There's a lot more intermediate concepts and things. So we take another course called Beginning Algebra. This is actually derived from how ALEKS works. These are all the concepts that the student was expected to learn in this course. And this is how all the concepts are related together. And then the 6 we were just talking about, you can see here, are distributed throughout the graph. So, again, depending on where the student is, which of these base concepts they already know, we can decide which ones they're ready to learn next. And then we can see, how you would find a large number of hypothetical paths in which the student could go through and learn all these concepts. Then you could take several courses in a curriculum that build on each other. In this case, multiple algebra courses, and then pre-calculus course, and maybe a course that even comes before algebra. And you can connect all those together, and you could see, okay, over a series of multiple courses, how all the concepts relate. So they take this course in the middle, which is called Beginning Algebra. It depends on concepts that you would have to learn in the prior course, and so on. And in some cases, there's overlap where in a given course, you might, there's some concepts that might appear in both of these courses if they overlap a lot. And then ultimately, the foundation of a class like pre-calculus is built on top of all these prior courses and all the concepts you would need to learn all along the way. Okay, so how does an ALEKS assessment actually work? So it's a loop. Um, we have to have a starting belief of what the probability a student can do any given question. And that's based on all the students that have taken the assessment previously. And so we make some default prior assumption on what all these probabilities are. Then based on the problems that we have the most uncertainty, we select a problem and see if the student answers it correctly or incorrectly. Then we update all the beliefs of all those probabilities like I described before. And then we continue this process until we've eliminated all the uncertainties sufficiently so that we can declare the specific subset or the specific feasible set of all the problems that the student can actually perform. So the final output is one of these feasible sets that we were talking about before. And what's amazing about ALEKS is that it can do this even for 200-300 concepts and about 25 to 30 questions, right? So it's, there's, as I'm sure you can only hold a student's attention on a math exam for so long before they get tired or before you're just asking too many questions, right? So, and it's sort of unclear maybe at the start how much information you could gather by doing an adaptive assessment. So I think it's kind of amazing that you can learn quite so much information about a student that you could say at the end of it, okay, of these 300 concepts, they know this specific 187, and that can be done in 30 questions or less. So there's a lot more details here that I'm not going to go into, but one of those questions is also a test question so that ALEKS can learn from itself and verify its assumptions and that the student population hasn't drifted over time. So there'll be one test question and then that can be used for calibration to make sure that it's still correlated in the way that's thought to correlate with all the other questions and so on. So it's actually slightly more efficient than this, but that's necessary to, pay attention to the student populations over time and how what they're being taught and what they know drifts. So the output of one of these assessments is what we call a feasible set, and that's this circle here that has the blue dots in it. And these concepts that are one step away from that set, that's this thing called the outer fringe. And those are the questions the student is most ready to learn next that I mentioned before. So ALEKS was originally designed not as an assessment mechanism for whether students are ready for a class or not. It was designed to be used alongside a course and help the student learn throughout the course. And to be able to do that, it was necessary for them to create this assessment procedure so that they could put the students on a personalized learning path, right? The original point of ALEKS wasn't actually to do these assessments for things like placing into university courses. It was more to be a learning companion that works alongside the student. And it was only later that people realized that this assessment mechanism itself has a lot of applications outside of this being used as a primer, basically, for a personalized learning tool. Okay, I'm going to pause here for any questions. I know I threw a lot of definitions and things at you. But if anyone has any questions, I'm happy to answer them before I slightly change the topic. Okay. Okay, so how did I get involved in this world? So I was at the University of Illinois with Allison, and we had this problem where a lot of our students, incoming students, were failing easy math courses, or I shouldn't say easy, but I should say like the first course that they were told they were supposed to take for their major, which might be pre-calculus or calculus or something like that if they were a science or engineering student, and they were failing this first class. At very high rates. And this is bad for a lot of reasons, of course. One, they can't take the classes that depend on these math classes. They can't take the science classes they need to take. They in some cases, like their scholarships might be threatened if they failed the math class because they didn't have a high enough GPA for their first quarter. It was expensive for the university to re-advise all these students and to reteach these students again and again. It's demoralizing for the student. It's bad for a lot of reasons, right? So Allison began looking for better ways to figure out who is actually ready for pre-calculus or calculus and how we can set them up, how we can tell students, here's the right class for you right now, so that we don't put them in a situation where they're set up to fail. So I say Allison and I. Allison was certainly the one that started the project, and I got involved a little bit later. But Allison, and correct me if I'm telling the story wrong, but you evaluated all the different like placement exams and assessments out there, and eventually stumbled across ALEKS, and had the idea to use ALEKS assessment mechanism to better determine which course our students should be taking. And then we later developed a specialized assessment. So originally there was I believe, oh, you have a question? Yes.
I'm going to ask that we don't do too much backwards and forwards yet, to just keep on schedule. So if it's just for clarification,
well,
it's going to be quick.
I did say you can ask questions, so let's please ask the question, but if yeah.
We can keep it quick, and then later we can lean into the tea time for deeper questions.
So please go ahead and ask the question.
Students, even if they can answer the questions, doesn't necessarily mean that
yeah.
Even if they got it right,
yeah,
that they actually answer.
Yeah.
I'm actually interested to know, what about those students, for example, let me just give you a quick scenario. In my case, I'm responsible for secondary engineering student. There's a course called linear algebra, differential equations. So mainly it's very abstract. So normally when we give questions like please and show that, that's actually the same question.
Yeah.
So because the course itself is very abstract, it's very easy, okay, from my experience, to tell that, okay, the likelihood of the students, whether they understood the question or not, based on how they answer, show that or prove that type of questions, because the course itself is very abstract. And how do you act?
Yeah.
When a student gets the questions right, it doesn't necessarily mean
right. Okay. So a few things. So one, the ALEKS assessment doesn't go quite that high into the math curriculum, up to like differential equations. But in the case of like the example I gave earlier, where it was a system of equations, there's more than one way to do it. Then if the student gets that one right, then ALEKS can ask other questions to try and target what they might have done. Like another question maybe that would ask them to calculate the determinant of a matrix or something like that. Then that would suggest that maybe they use Cramer's rule to solve that problem. Or it asks them another question that's known to be, again, highly correlated with like one of those subsets, and ultimately can tease out specifically what the student knows. For a more like a multi-step problem or like a proof-based problem or something like that, it would have to be broken down into pieces that the student can do individually, so that the output can be verified along the way. But ALEKS goes up to Calculus 1 now. Calculus 1 now is the highest course that we do. Now, I will say we did study our Calculus 2 and 3 students. And some other universities have studied them as well. And we found that the reason the students were failing Calculus 2 and 3, it wasn't because they couldn't do like basic derivatives and antiderivatives and so on. It was because they couldn't do trigonometry and like the arithmetic skills that were necessary to get the problem to a state that they could solve. So there's definitely correlations between the student just not having a sufficient underlying background to be able to do even some of these more advanced math classes. Go ahead.
So the ALEKS system has the CIs and QIs, concepts and questions, and all the intellects kind of mapped out as part of the system up to a certain level of.
That's right. And that's based on all the students that have taken assessments before. So it was originally based on expert opinion on, okay, to do this problem, you need these prerequisites. And they actually found that did not work super well. And part of the reason was because there's a lot of empirical linkages between questions that don't seem pedagogically logical because they're co-taught together. So like if a student can do a problem in trigonometry, they've probably seen problems in logarithms and so on. And so there's correlations there between those questions that are not strictly like logically necessary for one problem to depend on another one. So they ultimately used all the data they got from students taking the assessments to improve their knowledge of how everything is linked together. Okay, I have 5 minutes. Okay, so I'm almost done actually, so this is great. Okay, so we co-opted this ALEKS assessment basically to use as a placement exam at the University of Illinois. And it worked for our range of courses. I think we used the pre-calculus. There was a prep for calculus was like the existing ALEKS course that was about in the right range for us. Then we worked with ALEKS to expand and to basically say, okay, well, let's design an assessment specifically for trying to place students in the right course in university rather than just using one of the off-the-shelf ones. And let's have it do a wider range of classes, like all the way down to the most basic class that a student would take at a typical American university up to Calculus 1, Calculus 2. And then we gathered data for several years from the University of Illinois, and we partnered with several other institutions. And we analyzed the initial placement score with the final grades that the students got in the courses. And we found a direct and pretty strong relationship. And at the schools that implemented systems like we did, they often were able to reduce the fail rate by about 50%, which sometimes was from 50% down to 20% or 25% or so on. So this was not just a problem that we had at Illinois, it was a problem that many other similar institutions were having. And it wasn't something that just worked for us. When they were able to use our system, maybe with some small modifications, they found that it worked very well. And so now there are many publications with such data out there. This was initially it was in the US, yes. And then it did expand internationally. Like I said, I haven't worked with ALEKS in several years, so I can't tell you all of them, but I remember Kazakhstan was one of the first international schools, and there was a country in Canada and so on. So it started to spread throughout the United States and then beyond fairly quickly. So I just want to give you a little bit of a visualization of like what the output was. So I mentioned earlier that I said a couple hundred. So this is from the Prep for Calculus course that we used. It had 180 concepts, which are lined up along the bottom. And then whether there's a solid bar or an empty bar on the top chart means that for this like specific random student that I selected, they could do that concept or they couldn't do that concept, whether it's filled or not. So you can see the student could do like the first 4 or 5, and then there's, and they're roughly grouped together by like what kinds of questions they are. Are they about functions, or they're about geometry and trigonometry and so on. Then the middle plot is just the average of all the students in the class. So the darker it is, that means all the students in the class that could do it. If it's kind of in the middle color range, then about half the students could do it. And at the bottom, it's the middle chart, but it's split into the students that passed the course or failed the course. And so you can see the colors are a bit darker in the passed part than the failed part. So maybe that seems kind of obvious, but the students that knew more things at the beginning of the course did better in the course. And then you can even see which of the concepts have the most contrast, right? You can see some of the concepts are solid for both, so it didn't really matter. And some of them there's a much darker contrast. There's a much starker contrast between the two, which means that concept was particularly important for students to pass this class or not. And then ultimately, we were able to make a similar chart over the standard curriculum that we had. And you can see, again, the concepts are lined up on the bottom. I've split it here by what grade they got, A through F, A being the best. And then you can see, basically, if you pick a concept like the ones around 60 and you follow them up, you can see they didn't have much predictive power in what we call college algebra, but it started to have more differentiation in the next class up, pre-calculus. And then once the students got to calculus, pretty much everyone could do that question. So you can see exactly where in the curriculum a specific concept was important for students to know and to be successful in that. So there's much more to say about this, but I'm just about at time. If you want to hear more about it, please ask me later, or I can share some references with you. But I just wanted to show this as an example of what you can do with this output that you get from an adaptive assessment. That's more than just the final score that you get that I mentioned earlier, right? You gather a lot more information, and then that information can help you inform how you design your curriculum and all kinds of things later. That's it for me.